In the previous video, we talked about how to clean and pre-process texts and then how to create a document term matrix. And now in this video, we're going to talk about how you can actually use this document term matrix to do computational text analysis. We're going to distinguish three main branches of techniques. The first one is rule-based techniques. The essence of this approach is that researchers specify rules for how a computer should analyze text, so how it should measure certain kind of things. A typical example is the use of keyword search, where a researcher specifies specific words and word combinations that need to occur in a text. And then whenever this occurs, you can, for instance, say, well, then this text is about a certain topic, or this text has a certain positive sentiment or negative sentiment, what have you. Now, a second branch is that of supervised machine learning. So this broadly refers to the approach where a researcher provides an algorithm with some training data, and based on this data, the algorithm will train a model to perform a specific task. So in this case, the researcher does not provide the rules, it has the computer learn these rules itself based on a certain algorithm. There are several types of algorithms that can do this, from the basic but nevertheless powerful naive Bayes model to more state-of-the-art deep neural networks that you've certainly heard about when doing cool stuff in recent years. Finally, there's also the unsupervised machine learning approach. Here, researchers also train a model, but the training data does not specify a specific outcome that the model will learn to predict. Rather, an algorithm tries to find certain types of interesting patterns in the data, which is about as vague as it sounds, but we'll get to it. So one of the most popular examples here is topic modeling, which is a technique for automatically classifying documents into topics. Now, before we move on, please note that this classification is not definitive. There are some techniques that are hard to classify in these specific branches, and it's also not uncommon to combine techniques from multiple branches. Nevertheless, there is a clear conceptual difference between them, and it's helpful to recognize this in the various available text analysis techniques. First off, rule-based approaches. As just mentioned, the essence of a rule-based approach is that a researcher, or more generally a human, is the one who comes up with the rules. A good comparison here is if you think about a codebook in manual content analysis. So manual content analysis, the researcher operationalizes a certain kind of concept, then defines for coders what they need to look for, how they need to code this, what it means, how to think about it. With people, you can be quite touchy-feely about this, but when you do this for computers, you need to be very explicit in order for the computer to be able to do this task. So an example, as just mentioned, is keyword search, where you specifically say, well, this measurement is true if and only if this word or this combination of words occurs. And a similar kind of example is from dictionaries, for instance, the sentiment dictionary, where a researcher says, well, this word has a sentiment value of 0.6 or a sentiment value of minus 0.7 or something like that. In any case, it's about giving very explicit instructions for a computer on what value to code given specific conditions. And let me give you just a quick example of how to do a simple rule-based analysis in R. In this case, using a dictionary for a simple, keyword search. So we're going to use the quantita package, as we discussed also in the previous video on pre-processing. And first we're going to create a document term matrix. As input data, we're just going to use some demo data that's included in the quantita package. So if you open quantita, you by standard have this set which has some demo articles, which in this case is speeches, inaugural speeches from US presidents. Then you need to decide how to pre-process this data for your DTM. Well, important here is to consider whether the dictionary that you're using, whether the terms in the dictionary have also been pre-processed in certain ways. If these terms have been stemmed, you would also need to apply stemming in pre-processing your data. Now, often this is not the case, and in this case we're going to define the search terms ourselves. So we do not want to stem this stuff, we just want to use the exact words in our document term matrix. Now here we're going to specify a dictionary, and this is essentially the whole rule-based part. Here is the part where we specifically say, well, if you encounter a word that starts with terror, and then this asterisk is a wildcard, meaning it can end in any kind of way. So any word that starts with terror, terrorist, terrorism, etc. If you encounter that word, I want you to count that down as one occurrence of terror. And the same thing we do for economy. Whenever one of these words occurs, we're going to code it as economy. Now, of course, this is a very stupid dictionary. It doesn't really make that much sense. It's just meant to be a simple, short example. So here, we've specified our rules. And now we can use a function dfm lookup, which is a function which says apply this dictionary on a certain document term matrix. So here we're going to take our document term matrix, we're going to apply our dictionary, and here in no match is unmatched, we specify if a term is not matched, please still count it. So that afterwards we see how many words have also been not counted with the dictionary. You'll see that in a second. So now we've applied it. Basically what we get is a new document term matrix, but in this document term matrix, instead of having each term of the each term in the corpus be a column, the columns are just the results of our dictionary. So they look like this. So with a very silly dictionary example, we see that in the speech that Washington gave in 1789, there was no mentioning of terrorism. There was one mentioning of one of our economy terms, and there were 1536 words that were not matched by the dictionary at all. So this is just a very simple example, but I hope you get the gist of it. We can specify very specific rules and then apply those rules to perform a certain measurement. So let's move on with supervised machine learning. Just as with the rule-based approach, the goal of supervised machine learning is to have some kind of system which can then automatically, for a huge number of texts, perform a certain measurement. But in this case, instead of providing specific rules for how the computer should perform this measurement, we're going to provide the computer with some training data, which then contains the right answers, the thing that we want the computer to learn how to predict. And then we're going to have the computer itself find out what useful patterns it can find to make this prediction. So the supervision comes from the fact that we need to provide it with this training data. And this training data basically says, for some examples, what the correct outcome is. Now, a good example here is the one of spam filters. Now, say that you want to build a spam filter. And for sake of reference, imagine that you first want to try building a spam filter using a rule-based approach. So you start making a dictionary of terms which make it more or less likely that some kind of email should be classified as spam. So you're adding terms like Viagra, Saudi prince, maybe in combination with millions on bank accounts and something like that. But you quickly find out that there's a huge number of words to account for, many different kinds of combinations. So you realize that manually building rules for this kind of system is really a very difficult kind of task to do. So this is a situation where supervised machine learning can be really convenient, because then we just need one set of emails that we know are spam, that we have already labeled as being spam, and another set of emails of which we know that is not spam. This then constitutes our training data, and the idea of supervised machine learning is that with this data we can now train a model to help us classify emails as spam or not spam. So in a way, you can think of this as outsourcing the process of developing rules manually. You could also have given the training data to a student assistant, for example, and then told him or her to come up with rules for classifying emails as spam. But I mean, this would be expensive and also not very inspiring work for the assistants. So the benefit of supervised machine learning is that you can basically automate this kind of tasks. Now, how this works exactly, it depends, of course, on the type of machine learning model that is being used, but also, very importantly, on the data representation in which texts are provided. If texts are, for instance, represented as a document term matrix, as we discussed before, then the model will have to learn how to classify emails based only on the occurrence of words and word combinations. So let us do a quick example of this. Again, we're going to use the quantida package, but in this case we're also going to need quantida.textModels, which is basically an extension of the quantida package for some text models, which would include supervised machine learning models. Now we're going to create a document term matrix, which will be our data. For this, we're going to use the inaugural speeches corpus again. And then we're going to apply some basic pre-processing. We're going to stem the data. We're going to remove some stop words, and we're going to remove the punctuation. Now, a nice thing about quantida is that whenever you make a document feature matrix, document term matrix from a corpus, it also adds the document variables. So where we on the one hand have the matrix, the DTM, we also know for each row in this matrix, for each speech, who the president was, the first name, what the year was of the speech, party affiliation, and that kind of stuff. So now we want to add some kind of label that we're going to use for the prediction. And so we're going to do something quite silly. We're just going to say, let's see whether we can predict from a speech, from what is being said, whether the speech was made before or after the Second World War. And we're going to do this by simply adding a variable which looks at whether the year was before or after 1945. To be very clear about this, we now have an additional column in our document variables, which simply states, was a speech before or after the war. For reference, this is the same thing which you would have if you would have a set of emails. Then you might have some column somewhere, spam, which then indicates whether an email was spam or not. We can also have multiple categories. We don't have, it's not that we can only do true or false, but in this case, we're just going to focus on a simple binary case. So now that we have our data, let's split it into a training and test set. And this is a very common thing to do because typically when we develop these classifiers, we develop them in order to classify stuff that we haven't seen before. So we want to evaluate how well our model performs on data that is not included in the training data. Otherwise you get some overfitting issues. So what we do here is we're going to say, let's take a sample of rows from a document term matrix to create a training document term matrix. So here we basically say, take 40 of the rows from our DTM and make this a training DTM. And then in addition, we're going to say, we're going to make a test DTM, which is basically all the leftover rows. So all the rows that are not included in the train DTM. And here the set seed, in case you're not familiar with it, this sets a random seed. So this means that whenever we have some kind of random function following it, the results of this random function will always be the same, which is quite convenient for generating examples. And now we can get to the real meat of the matter, which is that we can train a text model, in this case a text model underscore MB, which stands for naive Bayes, which is a very classic classifier. It's not the best, but it's very simple and very powerful. So it's a good one to start out with. And here we say we're going to train on the training DTM, and what we want to train on is to predict this value, which is the document variable is pre-war. So in other words, we want to predict whether the speech was indeed before the war. Now we can use this model to make predictions. So here we use the predict function, which is standard function R. Then we're going to use the naive Bayes model as the thing to make the predictions with, and we're going to make these predictions with regards to the test data. So what we now have is a vector which says for each of the speeches whether it predicts that the speech was pre-war or not. So here it says, well, for the speech from 1793 by Washington, we do predict it was pre-war. And for this speech in 2017 from Trump, we predict that it was not from before the war, which in this case would both be correct. Now for a more general overview, a nice way to look at this is of course to create a crosstab of all the cases that were actually before and after the war and all the cases where we predicted it. So here we see the columns are whether a speech was actually before or after the war, and prediction is whether we predicted it to be before or after the war. And based on the diagonal, you see that we're actually doing quite well here. This means that accuracy is quite high. But to be a bit more specific, if we look at prediction, then we see that of all the times that we predicted something, a speech to be pre-war, which was in total 12 times, then 11 out of those 12 were correct. So this means that our precision is 11 over 12 or above 0.9, which is really good. And then if we look at the cases that were actually pre-war, that was 11 times, and all of those 11 times our model also predicted that to be the case. So our recall is actually 1, meaning that our model in this case performs really, really well. Now, of course, this won't be true for all data sets. This is exceptionally high, these kind of results, which just goes to show that apparently predicting whether a speech was before or after the war with this model is a very easy task to do. But the main thing here is to see that you have some quite simple codes that you can apply to already train one of these models and make some useful predictions. Now let's move on to unsupervised models. Now, if this is the first time that you hear of unsupervised machine learning, it probably sounds a bit confusing. The case of supervised machine learning at least makes a lot of intuitive sense. And supervised machine learning is also rather similar to the statistical models that we already know and love. So unsupervised machine learning as a text analysis approach is a bit weird because it implies that computers can somehow measure something useful in texts without requiring any supervision. In other words, that they can do this by themselves and therefore must have some sort of understanding of text, right? So no, not really. The idea is more broadly speaking that we can use an algorithm to find some useful patterns in data. And when I say that the unsupervised part of this is super nice, I'm also saying this somewhat tongue-in-cheek, because while unsupervised machine learning is certainly a very useful technique, we should be careful not to think of it as an alternative to supervised machine learning, where you do not need to provide training data with labels. Rather, it's just a very different technique with very different, but still very useful applications. An example that might help for, well, social scientists like myself is to first consider the case of factor analysis. So factor analysis, as you probably know, is a technique where we can find some latent constructs in our data. So imagine that you have a survey where you have asked many different kinds of questions, and they can, for instance, perform an exploratory factor analysis to see whether certain questions measure more or less the same thing. So the idea is that you can find some latent factors that explain the answers to these questions. For instance, you might find a factor which would measure political trust, and that could explain different answers to different questions. The same kind of thing can be said for the columns in the document term matrix. Instead of saying that all these columns contain a word, you might say that there is some kind of latent construct, such as a topic. And since a certain text is about this topic, the author tends to use certain kinds of words. This is again something which you could find out by looking at whether certain words tend to co-occur together often. Now, factor analysis is something that is sometimes being done in text analysis, so indeed you do see it being applied to document term matrices, but not so much anymore, I would say, because we do have techniques which are more specialized for text analysis, such as topic modeling, which is also a technique for finding these latent topics behind the corpus. Another example is scaling, where the classic example is that we might have different political manifestos and we want to organize them on some kind of latent dimension. And the idea is then that hopefully this dimension more or less approximate things like a political dimension between left and right or something like that. So as an example, as a more specific example, let's look into the idea of topic modeling. The goal of topic models is to have a computer come up with topics and then to classify documents according to these topics. For example, if you would apply topic modeling on a corpus of newspaper articles, you can automatically organize articles in categories that would ideally have some kind of relation to common sections in a newspaper. Behind sports articles, you would expect there to be some kind of latent topic of sports news, which would then explain the use of words such as football, competition, match, tournament. But the interesting thing here is that the computer won't actually know what sports are. It would simply look for patterns in the use of these words, based on which it indicates that they probably have some kind of shared topic. One of the most popular topic models at the moment is latent Dirichlet allocation, or LDA. By now there are actually many alternatives, and to be fair, most of them can often be better. But still, LDA is a good model to discuss because it is relatively easy to understand, and many of the more complicated models also build on the basic LDA approach. So in LDA, each word is assigned to a topic. And this is nice because it means that a document can actually contain a mixture of topics. Rather than saying that a document has the sport topic, LDA models each document as a multinomial distributions of all topics. Another nice thing about this is that words are not uniquely assigned to topics. A word can be assigned to different topics depending on the context in which it's used. For example, if you have the word nuclear, then in some kind of news articles it can be part of a topic about war and weapons, whereas in other news articles it can more accurately be part of a topic about energy generation. So the meaning of the word is actually also modeled within the context in which it is used. Now, I don't want to get too technical about how LDA works precisely, but just to give a general gist of it, I think this visualization is pretty nice because it shows how individual words in the documents are assigned to topics. So here the different colors indicate different topics, and how this makes up the multinomial distribution of topics in the documents. LDA is then basically based on two distributions, so we have these topic proportions per documents, but we also have word proportions per topic, because of course there is a relation between certain words which are more likely to occur in certain topics, such as football being more likely to occur in a topic about sports. And then the unsupervised part is the part where the LDA model tries to find distributions that fit the data. So if you give several thousands of newspaper articles to the algorithm, it tries to find distributions that fit these newspaper articles. So in a more layman's term, that's topic distributions that make sense given the data that it has seen. Now let's again run through a few simple example lines of code to show the general idea behind this. Again, we're using the quantita package, but we're also going to use the topic models package, which, as the name kind of implies, facilitates topic modeling. And before we're going to create a document term matrix, but before that we're going to split the inaugural corpus speeches into separate paragraphs. So just that we have several more articles to work with. This is mainly because for this example, for topic modeling, you really need to have a good amount of documents to properly model some good distributions. So here we're just going to artificially create more. Then we're going to create a document term matrix, again using some basic pre-processing. Here we use stemming, remove punctuation, and removing some stop words. In addition, what we're going to do is we're going to drop all terms that occur in less than 5 documents, or no, that occur less than 5 times. And the reason for that being simply that there are many of these words which only occur once or twice or 3 times, and these are not very informative for topics because they don't really tell us much. Their co-occurrence are just quite incidental. So in general, for topic modeling, there's also the reason that when you do topic modeling, you need to have a more or less limited vocabulary. If you have a large data set, you might be able to pull off like 10,000 columns in your DTM if you have a good computer, but at some point you'll run into computational problems. So you want to limit the amount of words in your corpus, and cutting off the words that occur least frequent is always a good way to get rid of the least informative words. Now also we need to convert our DTM to another type of DTM. So the topic models package actually doesn't play nicely with quantita. So quantita provides a convenient function to convert a DFM in their format to a document term matrix that the topic models package can work with. And really, once you have a document term matrix, applying training a topic model is really as simple as just running the LDA function from the topic models package on that document term matrix. And then we might have to specify some meta parameters. So here we want to specify that we're going to use GIP sampling. And very important for topic modeling, you often do have to specify yourself how many topics you want to get. This might sound quite arbitrary, and to be frank, it often is, because you don't know how many topics there are in your data. But this is something which, there are some ways to estimate what a good number of topics is, but often case you will have to basically decide this yourself, and then maybe run multiple models to see the results, to see what number of topics makes most sense. So we're going to train the model. Normally this can take quite a while. In this case, we're using a very small data set, so it should be done in a few seconds now. But if you're doing this with a large document term matrix, you might have to wait a day or two, depending on just how much data you're going to use. So also, as a fair warning, this model will not be very good, because to get proper distributions about word use, you really need many documents to train on. And now we just used a very small set for topic modeling. So a topic model, of course, can't say this topic is about sports. It can only say, well, here we have a topic in which these words tend to occur most often, or these words are most informative according to some measure. So if you want to inspect what kind of topics a topic model found, a typical first way to look at it is to just look at the top words per topic. So in this case, we had 10 topics. And for all these topics, we have some words which were most frequent in these topics, or which most informative for these topics. And then you can, based on these words, get some kind of interpretation of what these topics are about. And I say some kind because to do this properly, you really need to do some more proper validation, and there are some good articles on this. But for now, just bear with me for the bare essentials. We see that these topics have some words, and we can estimate whether there is some kind of topic in here. Now in the current data, you really won't see anything nice here because again, we trained on just very few articles, but even then you already see that it recognizes America and American are apparently two words that are part of the same kind of topic. A similar kind of thing here might be war and peace. This is being the stamped version of peace. So even with this small data set you see, and even a few seconds of training, you see that the model can come up with some kind of idea of topical structure and then organize documents according to these topics. So as a quick general recap of the main differences, in a rule-based approach, the researcher sets the specific rules to perform a specific type of measurement on texts. In a supervised machine learning approach, the goal is also to perform a very specific measurement, but instead of providing the rules for how to perform this measurement, the researcher provides annotated data from which the computer can then itself learn how to do this measurement. And the unsupervised approach is a bit of an odd one out here, because you don't really have this clear-cut measurement goal in mind. Rather, you provide some text to an algorithm, and then the algorithm finds some useful patterns that you can then use to perform certain types of analysis. A nice complementary way of thinking about the differences between these approaches is the one formulated by Bouwmans and Trilling. I'll put a link to the article in the description of this video. So they classify these three approaches on a scale from deductive to inductive, which I think is quite nice. So counting a dictionary, which is how they call the rule-based approach, can be said to be a very deductive approach because the researcher really has a clear idea what he or she is looking for and specifies how to look for it, how to measure it. And the most inductive would be unsupervised, because here you don't really have a clear idea of what you're looking for. It's more of an explorative kind of approach where you get new ideas or try to get new ideas. Of course, it can also be used in ways that align with deductive kind of research, but this does make sense if you think about the main thing that these techniques do. And then in between you have the supervised approaches, which on the one hand is very deductive because you have a clear thing of what you're looking for, but you're still more open about the ways that the computer will look for it. So I get how you can place this in the middle of deductive versus inductive. That's a nice additional way of thinking about this. Now, of course, the best way to actually learn this stuff properly is to do it yourself. So towards that end, we have 4 more videos with some short general instructions, short demo videos on different analysis. And in addition, and by we I mean Wouter van Attenveld and me, a colleague, we have a GitHub page where we distribute some R course material on various topics. So you can look at this link, and otherwise we also have some more specific links towards specific tutorials in the description of this video.